Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is part one in a series on applications of integration and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view Introduction to Integration prior to watching this video. In this video, we will be discussing compound regions, regions between curves, and integrals with respect to y. In previous lessons, we calculated the area under a function using integrals. For some functions, it is easier to split the region into two or more segments that may be added together. In the graph to the right, we have the function f of x is equal to the absolute value of x. Since the absolute value function cannot be integrated as is, we need to express it as its piecewise function, f of x equals negative x for x less than 0, and f of x equals x for x greater than or equal to 0. In this way, we can evaluate the area under the function on the interval -1 to 1 as the sum of the two pieces of the piecewise function, or the integral from -1 to 0 of negative x dx, plus the integral of 0 to 1 of x dx. When we take this integral, we have negative x squared over 2 evaluated from -1 to 0, plus x squared over 2 evaluated from 0 to 1, which gives us negative 0 squared over 2 minus negative 1 squared over 2, plus 1 squared over 2 minus 0 squared over 2. When we take the 0 parts out and simplify, we are left with 1/2 plus 1/2, equaling 1 square unit of area. As another example, let's find the area under the two functions y equals sine x and y equals cosine x on the interval from 0 to pi over 2. Just as in the last example, we can divide this integral into two parts if we split the interval at pi over 4. So we take the integral from 0 to pi over 4 of sine x dx plus the integral of pi over 4 to pi over 2 of cosine x dx. The antiderivative of sine is negative cosine, evaluated from 0 to pi over 4, and the antiderivative of cosine is sine, evaluated from pi over 4 to pi over 2. From here we get negative square root of 2 over 2 minus negative 1 plus 1 minus square root of 2 over 2. When we simplify, we get 2 minus square root of 2, or approximately 0.586 square units of area. In previous lessons, we learned that the integral is used to calculate the area under a curved function. In the graph to the right, area equals the integral from a to b of f of x dx. We can do the same thing if we have a g of x and find the area under this curve in the same way. Area equals the integral from a to b of g of x dx. So now let us say we have to find the area between the two functions f of x and g of x. This is simply the integral from a to b of f of x minus g of x dx. As an example, let's find the area between the two graphs y equals the square root of x and y equals x on the interval from 0 to 1. From the graph, it is easy to see that the square root of x will cover the larger area between the function and the x-axis. So to find the area between them, we subtract the area under f of x is equal to x from f of x equals the square root of x. Therefore, the area will equal the integral from 0 to 1 of the square root of x minus x dx. When we take the integral, we get 2 times the square root of x cubed over 3 minus x squared over 2 evaluated from 0 to 1. From this, we get 2 times the square root of 1 cubed over 3 minus 1 squared over 2 minus the quantity of 2 times the square root of 0 cubed over 3 minus 0 squared over 2. When we simplify, we get 2/3 minus 1/2, or 1/6 square unit of area. Some functions are easier to express with respect to y, essentially reversing the function. In this example, we can take the integral from 0 to a of f of x dx, or the integral from 0 to b of f of y dy. As an example, let's evaluate the area between the two functions y equals the square root of x and y equals x cubed. When we graph the functions, we see that y equals square root of x lies above y equals x cubed with respect to the x-axis between the 2 points where the functions are equal, 0, 0, and 1, 1. Therefore, we take the integral from 0 to 1 of the square root of x minus x cubed dx. Here we get 2 times the square root of x cubed over 3 minus x to the fourth over 4, evaluated from 0 to 1. When we do this, we get 2 times the square root of 1 cubed over 3 minus 1 to the fourth over 4 minus the quantity of 2 times the square root of 0 cubed over 3 minus 0 to the fourth over 4. When we simplify, we get 2/3 minus 1/4, or 5 over 12 square units of area. Now let's look at the same example, but evaluate the functions with respect to the y-axis. Solving both for x, we get x equals y squared and x equals the cube root of y. Note that these equations are only inverses of the previous equations on the interval given 0 to 1. This one differs because if you look at the graph with respect to the y-axis, the cube root of y is above y squared. So we take the integral from 0 to 1 of the cube root of y minus y squared dy. And the interval is taken from the y-axis 0 to 1. When we take this integral, we get 3 times the cube root of y to the fourth over 4 minus y cubed over 3, evaluated from 0 to 1. This leads to 3 times the cube root of 1 to the fourth over 4 minus 1 cubed over 3 minus the quantity of 3 times the cube root of 0 to the fourth over 4 minus 0 to the third over 3, which simplifies to 3/4 minus 1/3, or 5 over 12 square units of area. Note, this is the same answer as when we evaluated it with respect to x. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.